We present SPIn-NERF, Multiview Segmentation and Perceptual Inpainting with Neural Radiance fields. Our model begins with transferring a set of sparse pixel-level annotations to a multi-view mask and uses it to enable novel view renderings of an inpainted scene. Given multiple captures of a scene and their corresponding camera poses, Neural Radiance fields use volumetric rendering to generate state-of-the-art novel views. In addition to the conventional NERF inputs, we ask the user to interact with a single view to tell us which object they want to remove. In this particular example, the user is selecting the statue with a few clicks. All of the views in addition to the source mask are then given to a video segmentation model to get an initial set of 3D inconsistent masks. A semantic NERF is then trained to come up with a 3D mask, which is the output of our multi-view segmentation model. A semantic NERF is an extended neural radiance field where in addition to a color and density, it returns the semantic logit for every point and view direction. For fast convergence, we follow the architecture of instant NGP and use a multi-resolution hash encoding and spherical harmonics. Notice that similar to density, objectness score is also view-independent, while colors are view-dependent. The colors and densities of a semantic NERF are supervised using volumetric rendering and the typical reconstruction loss as in NERF. To train the semantic scores, first the pixel-wise pre-sigmoid semantic logits are calculated by substituting the point colors with semantics in the volumetric rendering equation. Then the binary cross-entropy loss between the rendered objectness scores and the initial masks is used to update the semantic NERF. Note that while calculating the classification loss, the densities are detached to prevent inconsistent masks from forcing the geometry to converge to some degenerate solutions. This approach starts with the view inconsistent initial masks and projects them to the space in a geometry-aware fashion. In practice, we use a two-stage training process to further improve the masks. Using this NERF, we render the training masks and disparities from the scene that are then given to an off-the-shelf 2D inpainter to come up with a geometry and appearance guidance for the inpainted NERF. While the mean squared error is used to supervise the geometry, since the outputs of the 2D inpainter are 3D inconsistent, a perceptual loss is used to supervise the appearance. To reduce the memory footprint and increase the speed of the fitting process, the perceptual loss is calculated between smaller random patches sampled from the bounding box of the object mask. The perceptual loss relaxes the hard reconstruction constraints of NERFs and prevents blurry results while creating view-dependent effects. In this 2D toy example, based on a sample image and a synthetic square mask, we first generate 16 different inconsistent but plausible inpaintings. Then we optimize an output based on these 16 inputs. In the first approach, MS loss is used, while on the alternative approach on the right-hand side, we use the perceptual loss to fit the output image. As evident in the results, using the perceptual loss helps to handle the inconsistencies and generates a more detailed texture, while in contrast, the MS loss has led to a blurry and fuzzy output. Here we show more segmentation and inpainting results. Notice that both the multi-view mask and the inpainted scene are rendered from novel views that were not seen during the training. We argue that it is important to use the inpainted information from multiple views. In this example, notice how the color of the inpainted region changes with respect to the camera movement to represent a reflective surface on the piano. Here, the inpainted region behind the flower pot becomes darker in certain views to make it look consistent with its surrounding. Moreover, notice the accurate reconstruction of the repeated fine structure in the background. For quantitative evaluation, we address the need for a standard benchmark including ground truth captures of scenes without the unwanted object as test views and introduce a dataset containing 10 real-world scenes with human annotated object masks. For each scene, we provide 60 training images with the object and 40 test images without the object. For every scene, all of the 100 images are then fed into Colmap in order to recover the camera parameters in a shared coordinate system. This dataset is further suitable for evaluating tasks such as real-time 3D inpainting, unsupervised 3D segmentation, and video inpainting. Thank you very much for your attention. Please visit our website for more examples and our paper for details. We have also released the code and dataset on our website.